application of 3D printing in radiation oncology and medical physics. Just little bit about the topic. Earlier the traditional machining technology, that is manufacturing technology, the 3D objects are manufactured by subtracting a layer by layer. Finally, we will get a 3D object. In contrast, at present, the additive manufacturing technology, it is a method of creating a three-dimensional physical object from a three-dimensional digital model, typically by adding many successive thin layer by layer using a CAD, computer-aided design, or a computer-created design. So this additive manufacturing is known as the 3D printing. I hope Dr. Paul will be presenting in detail. As of today, I think 3D printing been already developed in various industries like consumer product, electronics, automotive, aerospace. At the same time, 3D printing is recognized as an effective tool in clinical tool in healthcare. Also, it is rapidly growing in radiation oncology. The most common 3D printing applications in our field include QA phantoms, brachytherapy applications, bolus, compensators, etc. So with this small background, today we are going to listen more details from Dr. Paul Ravindran presentation on this topic, application of 3D printing on radiation oncology and medical physics. Okay. Just before going into the topic, bit introduction about the speaker. He's a known person to all of us, but still it is customary to introduce. Can you hear, sir?
I can, yeah.
Yeah. Dr. Paul Ravindran is a retired professor of radiation physics from CMC Vellore, India. Currently working as chief medical physicist at the Christian Institute of Health Sciences and Research, Dimapur, Nagaland. He has more than 35 years of teaching experience in medical physics. He has been teaching radiation physics to radiation oncology residents, postgraduate medical physics students, and radiotherapy and imaging technology students. He is instrumental for various developments in his department at the CMC. To mention few, starting a 3-year MSc program, Dosimetry lab, etc. He has great passion for teaching, and his interactive style of delivering lectures in our field made him a professor much loved by most of us. I hope all of you agree. He also served as a vice principal of Allied Health Sciences of CMC Vellore for a period of 4 years. Dr. Paul Ravindran has significant international experience and has worked at the London Regional Cancer Program, London, and also worked in Canada for 2 years. Dr. Paul Ravindran was awarded a Fellow of Canadian College of Physicists Medicine. He has vast experience in academic, clinical, and research activities and has been involved in numerous projects as a principal investigator. Many students have received their doctoral degree under his guidance from Tamil Nadu MGR Medical University, Chennai. He has more than 50 scientific publications in peer-reviewed journals and has conducted many workshops and conferences. Apart from this, Dr. Paul Ravindran has served as an expert for several missions of IAEA to various countries in South Asia and Asia Pacific region. He also served as consultant to IAEA for a year during 2019-20. He has received the Outstanding Medical Physics Award from the Asia Oceanic Federation of Organization for Medical Physics. He is a member of editorial board of JMP, a member of DST Projects Review Committee, and a member of high-level expert committee of Department of Biotechnology. Dr. Paul has much more credentials, but due to time factor, I stop with this. Now let us start with the presentation by Dr. Paul Ravindran. Before that, just a few announcements. Feel free to drop your questions on the topic to the chat box. You will get answer at the end of the presentation. Also, don't worry about making notes immediately. You will be uploaded with the session recording. So, without further delay, let us listen to Dr. Paul Ravindran. Dr. Paul Ravindran, please.
Thank you, Dr. Ved Morgan. Am I audible? Yeah. Thank you very much for the very, very generous introduction. I don't think I deserve anything more. And dear colleagues, thank you for joining. Before I start, I would like to have some disclaimers. Number one, I'm not an expert in 3D printing. The story behind this talk is some 6 months ago. This is actually my retirement plan. After retirement, I thought I should get a 3D printer and do whatever I like with. But I took up also a job, but still I didn't want to stop my retirement plan. I got the 3D printer at home and started doing it. And what I'm going to talk is what I learned during the last 4 to 5 months, like somewhere from December to now. So this is a disclaimer. So I'm not an expert, but this made me look at something. So I thought I will share with you all those. Already some introduction to 3D printing has been given, but for the sake, I will also do. I will talk about what is 3D printing a little bit, and then the history of 3D printing. And 3D printing in radiation oncology and medical physics, which is the core topic for today, with basically something like bolus making, immobilization devices, and phantoms. And what we do at CHSR Dimapur with 3D printing, that's another interesting thing that we would like to share with you within the last few months, what we could achieve. I will also show you a couple of 3D printing videos to take you through the process, and then I will do a conclusion. Right. So what is 3D printing? As it was explained by the chairperson today, 3D printing is also called additive manufacturing. So I will be using the term 3D printing and AM, additive manufacturing, on and off, like I will be changing from one to the other. So don't get confused, both mean the same at the moment, right? A three-dimensional object is created by laying down successive layers of materials. I'll try to explain you that in little more detail as we go through. And it is achieved by an additive process and is called additive manufacturing. And that's the reason it's called additive manufacturing. 3D printing is a layer by layer manufacturing process that directly produces an object from 3D digital data. So you should have a 3D digital data to do 3D printing. Going back to the history, the 3D printing was introduced by someone called Charles Hull in 1984 to 86. He coined the term stereolithography for the method he was using. And the first 3D printer was built around 1992 by 3D Systems. And first application of 3D printing in medical field was creating a human bladder. So not only, that the radiotherapy has started using 3D printing a little later, but the 3D printing in medicine has been there. We will just look at the workflow first and then go into the details. So we said about 3D printing. Number one, you should have a 3D digital data. So this 3D digital data can be created by multiple means. One is using a CAD software, computer-aided designing software. So if you're already familiar with that, of course, you are almost halfway through to the well, and you will be able to finish 3D printing, get to know 3D printing much faster. And then you need to convert the 3D model into a 3D printer readable format, which is generally referred to as a G code, .G code, which is computer numerical control code, programming language, where the computer can provide instruction to the motors and how to rotate and things like that. That's referred to as a .G code format. So once you convert to .G code format, then it is ready for 3D printing. And then the 3D printer prints that layer by layer. There are different methods of 3D printing. As I said earlier, the first method suggested was the stereolithography, which is usually referred to as SLA method, and selective laser sintering, and fused deposition modeling, which I am using and most of the people are using, because this is a very cheaper way of doing. You can get a desktop 3D printer. I will show you that you can use in your laboratory or house, even house. I have it in my house, okay? And then color jet printing, which is referred to as CJP, and multi-jet function, polyjet function, and direct metal lasers sintering. And there are few more methods which are not very common in medicine, so I just left it there. So looking at the accuracy of it, you can see that stereolithography is the most accurate. The one I'm using as the forced deposition modeling is less accurate in the list, but still I find it to be very accurate compared to what I need actually. And the materials that is used for 3D printing, which we call the filament, could vary. It could be thermoplastic plastics and metals or ceramics and photopolymers. There are different things, and metals people use. There are different things are used. The application, if you look at from the method, is surgical. This SLA is usually a surgical tool, and selective laser sintering is used in medical implant, and the FDM is mostly a phantom making, and CJP is also in phantom making. Again, multi-jet fusion is used in surgical tool, but it's not that. It is, these are some of the applications which most people have tried to use. You can use for different things. That's not that this method is fixed for this. It's not like that. And polyjet is for phantom. People used phantom making, and DMLS is medical implants people have used. And this gives the thickness of the layer, which basically tells you how fine is the printing. As you can see here it is 0.025 mm, whereas if you go to FDM, it is 0.127 mm. So naturally, this is much more accurate than this method that I'm using. So I will explain you how the method that I'm using works. And this has got a filament, which I said could be a thermoplastic. The one I use is called PLA and the polyacetic acid and ABS. Okay, so these are the thing. ABS is a little difficult to use, but PLA can be used much conveniently. And this comes in the form of a wire which is fit into the 3D printer, and there is a feeder here which feeds it, and then it goes to a nozzle which makes it very thin. It's the 0.5 mm nozzle, and it is heated to about 200 to 240 degrees centigrade depending on the material here, and then it drops the material onto a bed which is called the heating bed. The bed is also heated so that it sticks, the material sticks to it. So this is that heating bed. So this is actually the 3D printer that I have, and very cheap model, desktop model. It is about 17,000 rupees that I bought it for. And you can even get it lower or a little higher, but everybody can afford to have it. This is the spool in which the 3D filament printing filament is there, and this is the driving mechanism, and it has got X, Y, Z movement, and very simple to do it yourself 3D printer. Now, the first thing in 3D printing is you should have a 3D model for printing. As I said, you can use a CAD software for it. And most medical physics applications for making templates for brachytherapy or phantom, you will need a CAD software. You need to learn how to use a CAD software. It's not difficult. Think about this. A person who is retired in life can learn CAD to some extent in the last 4 months, and you all can master it in few months, right? So it's not a difficult one. And several CAD softwares are available. Some of them are free, like FreeCAD is you can use. I'm using something called Autodesk Fusion 360, which is partially free, and it works on a cloud, and I find it to be very comfortable. I may switch over to FreeCAD, but I'm just exploring both now. For other medical applications, you need the 3D data can be taken from CT or MR or even PET CT or PET MR. But this is relatively difficult compared to using CAD. CAD, if you learn, you can use it, but here you have to extract the model that you want. I will show you one model that I made, but I made it easier with some softwares. And then the other method you can get the 3D data is optical imaging. I'll talk about this little later, that you can get the surface data by optical imaging. So you know how to get the 3D data. Now you can use either a CAD software or a CT data or optical imaging, and then you have to convert into the code that is printable by 3D printer, and then 3D printer prints it. So simple as that. So, but in medicine, let us look where all they have used. 3D printing is applied with several branches of medicine. And 3D printing in dentistry is very common. Dental molds are made, implants are made. And maxillofacial surgery, actually one maxillofacial surgery was visiting my office in Dimapur. When he saw some of the 3D printer model, spine model, I had it on my table, he was surprised. Like he uses it so much for his surgery, but he saw something on my table. He was asking, how come you are using this? Right. And then medical 3D printing for radiologists is possible. There is a good lecture on the YouTube by the Houston hospital, that hospital in Houston, and you can listen to that. But it's a long lecture, but there's a significant amount of information there. And 3D printing in modern cardiology is there. Bone implant scaffolds for tissue engineering applications are also possible. Let us come to 3D printing in radiation oncology and medical physics. I will not leave medical physics. I'll always include. I'll tell you there are something which is only for medical physics. So I put 3D printing for radiation oncology and medical physics. One of these is quality assurance phantom, right? You can make quality assurance phantom not only for radiation oncology, even for diagnostic radiology, right? I have in my mind some quality assurance phantom that I can make for diagnostic radiology. And brachytherapy applicators is one where it can be used. And bolus for photon radiotherapy, electron, you can make bolus as well as electron cutouts people have made. You know, normally we make with low melting point alloy, but you can use 3D printing to make any shape of electron cutouts. And proton was the first one to be used actually. Proton radiotherapy bolus have been made. Compensator blocks can be made, immobilization devices, beam modifiers, and it's left to your imagination of what next you could do it. That's why what I said I will be using the word additive manufacturing and 3D printing alternatively. So here it is additive manufacturing in radiotherapy. There are several things. There is a review paper by Ms. Rooney et al. Where they have analyzed where all people use additive manufacturing or 3D printing in radiotherapy. And in their analysis, they found quality assurance phantoms were 26%, brachytherapy applicators were 20%, and bolus making were 17%, animal irradiation 10%, compensators 7%, and immobilization devices 5%. Right? And there are other few more applications which are not included in this list. So they have did a very good review. You can look at this review and see what for they have used 3D printing have been used so far. In radiation oncology, as I said, the first attempt was by Zhu et al., who made low-cost proton range compensators. You know, you use range compensator in proton beam therapy, and they made low-cost range compensator, and they found 3D printing to provide very good geometrical accuracy than milling machine compensator, the compensator used from milling machine. And it reduced the cost of making the compensator, and AM took 6 times the time of milling machine. You know, additive manufacturing or the 3D printing takes much more time than the regular thing. So I will talk about the time a little later. And using the additive manufacturing process not only reduces the cost of fabrication of compensating devices, but it also enables the development of more complex geometries. You can make any geometry easily that you want. The other thing is bolus making. The first few slides, most of the slides will be like going through what is there in the literature, in the research, in people have done. And then at the end, I will go to as I said, few things that we have done. Boluses are used in high-energy radiotherapy, as you all know, and to overcome the skin sparing effect. Bolus with materials of tissue equivalent properties are usually used to shift the dose distribution towards the skin. Normally, we use bolus and they fail to make a perfect contact to the skin at certain points. For example, let me say you are making a nose bolus, there will be an air gap. Sometimes even in breast bolus, people see a air gap. So these air gaps will have different dosimetry at that point. So this has to be addressed. And the material used for 3D printing of bolus could be a concern. And so one has to choose a proper material. Several substances have been tried, and it has to be odorless, non-sticky, and it should be harmless to the skin. Right? People have used the PLA and the ABS and found this to be hard and could not be used with the sensitive skin. In certain skins, these could not be used. And Clearflex and Aguilar's and rubber-like photopolymer resins were quite useful. People have tried that also. But the only issue is it also depends on which 3D printer you use. All printers may not take every filament. So you have to be careful in choosing that. Looking at the workflow, actually I took this pictures from Shinwook's paper on the workflow of 3D printed bolus. You do a CT of the patient, draw the bolus and create a structure, bolus structure, and then transfer it to a segmenting software. I will come to that later, and then send it to a 3D printer. You get the 3D printer. But the problem here is people want to do the planning CT with the bolus. So then it is fixed onto the patient and the second CT is taken. So this is one of the issues people talk, but in my opinion, that is not needed. Two ways by which you can overcome. One is you can find out the Hornsfield unit for the bolus material that you are using by 3D printing and input that when you do your planning. So that will take care of it. The other method I will discuss now is to go for optical scanning. So the second CT to be avoided, one can do optical scanning. There are optical scanners that are available commercially, not very expensive though, about ₹1,00,000 you can get a good handheld optical scanners, which you can use to get the full 3D surface. And this can be converted to G-code to develop the 3D printed bolus. I will give you one suggestion here that you can use other optical scanners. You can try to use other optical scanners that are now used in radiotherapy also. 3D printed patient-specific immobilization devices. This is another thing where people have tried significantly. There is a good review paper by a group from Australia in Peter Mac. They have done a review on the immobilization devices that are being used. You need to have an accurate immobilization to guarantee that your dose distribution is to the target is accurate. Immobilization of head is most commonly accomplished by thermoplastic mask. Occasionally, the masks are combined with bite blocks also. Sometimes you need to provide a bite block or a tongue depressor thing. And most important attribute of immobilization device, it says intrafraction and interfractional accuracy. How accurately it holds it during the treatment and between the fractions. And 3D printing or additive manufacturing can be used to develop immobilization devices and also the both bites. This is the one that I told you about, a good review about immobilization devices by 3D print. This you can make a patient-specific immobilization device, and they have seen about 18 people. I think it is about 18 papers. I don't remember exactly. And they found that human objects were 61% and animal subjects were 22%, and phantom studies were about 11% in what they have seen. And these are some of the things immobilization devices tried. One group here, MF Hafner et al., performed a feasibility study in somewhere in 2018. I'm stressing the period here. And what they did was they took about 8 volunteers and did MRI and made 3D printed mask and also the base plate using the MRI, using the MRI data with the 3D printer. And they acquired the MRI, did and processed it and did a 3D print. And they tried it with repeated thing. But this, the base device was developed using a CAD software, and the mask was developed using the MRI data. And few years later, they came up with another paper, the same group, with clinical experience on 3D printed mask, and they studied 6 patients with whole brain RT with 3D printed mask and concluded that 3D printing provided a reliable and reproducible interfraction positioning accuracy. So this is the same group. In 2018, they tried, and 2021, they have come up with the clinical experience. And the another group, they made immobilization, but little, I think, is not a very easy way, but it is interesting to say. They took a previous CT scan of the patient who is coming for RT, and they did the model of the patient, 3D printed the entire model of the head model of the patient, and then did a thermoplastic mask that we do regularly for this model, and they placed it on the patient when they came for treatment or the CT planning. So this way, their argument is you can avoid the visit for making the immobilization thermoplastic mask. Otherwise, in my opinion, it's little roundabout and cumbersome because you have to make the model. It will take significant amount of time. And just making 3D printed immobilization is not enough, or bolus is not enough. You need to commission it clinically. See, as a physicist, you must be interested in doing it. Here is a paper by Tyler Mayer et al., where they have said what are the things you should do for commissioning a 3D printed immobilization or 3D printed bolus. So you have to study the attenuation composition of the with the TPS and tissue equivalency, and also perform surface dose measurement with that, so that you can know what is the dose to the skin when you use a particular material for 3D printing of immobilization device. The other thing is the immobilization of the tongue. This is a factor of uncertainty, is the mobility of the tongue and the base of the tongue, because there is usually no fixation during RT. We used to do that, actually extra dose here could result in oral mycositis, and this is a problem. For that, we try to take the tongue away from the radiation beam, and for which we use a tongue displacement device. We used to call it tongue depressor or tongue retraction device for head and neck radiotherapy. People have made custom-made tongue depressors or tongue displacement device by 3D printing. And this is one of the places where it has been found quite useful. Here is a 3D printed tongue displacement device by this group of Ju et al. And they have used this for nasopharyngeal cancer patients. And Thomas Held et al. Also developed 3D printed tooth bone tissue retraction device. There are quite a few people who have worked on this tongue displacement devices with 3D printing. Advantages of 3D printed immobilization device. I looked at the review article by Asfia et al. And they have studied that the improved patient comfort has been said by 4 of the reviewed papers, and reduced patient visit to the clinic. 3 of them have said elimination of the stressful thermoforming process, making the mask that we do regularly, and 4 people have commented that that has eliminated. High accuracy and tolerance to the patient, repeatable positioning accuracy, less damage to the surrounding healthy tissue, similar beam attenuation properties like the one that we use regularly, and opportunity to consider additional features to improve fit or patient engagement. So these are the advantages in 3D printed immobilization devices as per the review. And also there are some disadvantages, one being 3D printing process to negatively influence the material behavior, and inaccuracies due to conversion of scan data. When you take from CT scan, when you got to do a proper conversion, if you do any mistake, then there could be inaccuracies. And the process is slow because printing takes long time, and lower accuracy compared to surgical immobilization. But anyway, it is better than what we are doing now. And the cost that may be the same or higher than traditional immobilizations. And 3D printing has also been used in brachytherapy. The variation in contour in some patients and the steep physical gradients in regions like the head and neck needs customized brachytherapy solutions. This is the argument for 3D printing. Additive manufacturing or 3D printing offers accurate and reproducible mold. You can see this is one of the mold that has been made for surface, which I took from Robert Bell's paper. And he did a review of about 28 publications on additive manufacturing in superficial skin brachytherapy, and people who have been using it, and it has been found to be quite useful. Dosimetry in 3D printing, the interesting thing is when it comes to dosimetry, people have tried to make patient-specific phantom for patient-specific QA. And here is a work where Kim et al. Have done a spine-shaped phantom. This is what done by SK, and they placed it inside the, another phantom so that they could do a dosimetry with this. And this is a spine phantom printed with the DLP and polyjet, not by the FDM technology that I have been using. But I also did a spine phantom. This is the spine phantom I did. This is not actually a spine phantom. It's a spine model. I just wanted to see whether I can print from CT. So I did this and it was quite successful. This is a spine model that I printed with my low cost 3D printer. And in radiotherapy phantom, there is another phantom created, which is called, which by the Woods et al., who made a 3D printed QA phantom for 6 degrees of freedom verification of the 6D OF couch. And that's why it's quite long. So they wanted to make sure that it is helpful in finding, because you normally don't rotate more than 3 degrees, right? So it must be able to find out that variation. And then it's long. And this has been used, 3D printed and used. And another very interesting 3D printing application in dosimetry is in making ion chambers. This is the ion chamber array that has been tried by Bravio et al., who demonstrated that there could be a 3D printing technique could be used for fabricating ion chamber arrays in clinical use in radiotherapy application. There is a nice paper by him there. And in CMC Vellore, before I retired, we started a project, but they did it after my retirement. They did a phantom by 3D printing with the local engineering college, and they 3D printed from a patient CT, as a pediatric patient CT. And this is the phantom, and the organs were filled with gelatins to, they had the organs simulated with gelatin. We do gel dosimetry, so they had gelatin, they filled it here. And they made a full phantom, like a random phantom. So this is possible with 3D printing, right? So this was developed at CMC Vellore a year and a half ago. Let us now come to the core thing, what we have been doing in, say, HSR. After I bought the 3D printing, we did two things. One main thing. One is to make a phantom for quality assurance of IGRT equipment, and another workflow we established for making bolus, particularly the nose bolus. How did we do that? And as I said, I learned a CAD software called Autodesk Fusion 360. I made a 12 by 12 centimeter cube. This is the one, and we made this laser marker here, so you can use it for laser alignment. And then, sorry, this is not working, but it should, the video, it should work. I'm just looking at why it's not working. Okay. Anyway, so this is the phantom, and then this is exactly the phantom being 3D printed here, as you can see. And this can be used for IGRT QA. And the workflow is, we did a CT of this. We did a plan with the central. This has got 5 radio opaque balls in the 5 poles that I have kept, one at the ISO center. And with this, we should be able to make a plan with the center ball, and then off center it, and then do that alignment using IGRT and see whether the couch movement is correct. The center ball can also be used to do WL test that is used in radiosurgery. So this phantom is being made. Actually, I did one which was successful. The second one was not very successful because my learning curve in 3D printing is still not complete. I made some mistakes, and we are now working on that more. And the second thing we tried was to get a workflow for bolus. What we did was, we did a bolus printing on the TPS with 5 mm thickness, and exported it to 3D slicer software, which is again free scientific software. And in the 3D slicer software, we could segment and export it as Dot Stl File. Then we move it to the slicer software for 3D printing, which will convert Dot Stl to Dot G code file. And I actually use something called Ultimaker Cura, but normally when you buy 3D printer, they also give you one. I find this to be more useful. And then you move the Dot G code file to the 3D printer, you can get that printer. You can see that being printed here. And we wanted to do this little bit of dosimetric study about the PLA and the ABS that we could use for 3D printing, particularly with reference to bolus. So what I did was to make some slabs of different thicknesses of both the PLA and ABS, but with ABS I got a lot of difficulty because of the sticking. It was not sticking to the bed, and it was coming off, and I couldn't really make many. But with PLA, that was not a problem. I could make nice slabs of different thickness, 1 mm, 2 mm, 3 mm, 5 mm. And this one, I could make 1 mm and only 1 5 mm. So one thing when you do the dosimetry slabs is, you have to be very careful. When the 3D printing methodology is that there is something called infill. The percentage infill is usually about 20 to 30 to reduce the amount of printing and the time of printing. So you can see there is a honeycomb structure made. When I say 20% infill, it will not fill up the entire block. If you are making a block, it will not fill up the entire block. It will have something like a honeycomb thing. It's called infill. And this is a 20% infill. If you do a 20% infill and use it for dosimetry, that's not correct. So when I did this for dosimetry, I had 100% infill. It is completely filled with the
Recording stopped.
material that we use. And that is the PLA that we are using, or the ABS. So please remember, when you want to do dosimetry, please have it as much as 100%, if possible 100%, at least some 90 to 95% infill you should have. So with this slabs, we did the surface dose, and as expected, the density of PLA as stated by the manufacturer is 1.66. But I think it is not very correct. We need to check that ourselves. So that's why we did it. And ABS is almost equivalent to water. It's 1.04. So, and truly, when we did that, the Dmax got shifted for PLA to 10 mm from 15 mm for a 6 MVB. Whereas for ABS, it was about 15 mm. So our calculation seems to be correct. But to ensure that this is right, we did the CT of both the slabs that we have, PLA as well as the ABS. And we looked at the Hounsfield unit. The mean Hounsfield unit for PLA was about 172 with the standard deviation of 54, and for ABS is minus 75 with a standard deviation of 28. So this is what, in my opinion, when you do a bolus with the CT, with the treatment planning, by drawing, you can enter this value, mean value, as the Hounsfield unit there, so that the calculation is taken care of. You don't need to actually do a second CT. But of course, you can use optical method that will be more convenient and easy. This is a video. I will next 2 slides, I will take you through video how we made the bolus. You can see the bolus is being drawn on the TPS in an eclipse TPS. We drew the bolus. And this will tell you the workflow. That's why I have the thing. And the bolus thickness you will have to define on this. As I said, we defined the bolus thickness as 0.5 centimeters. So we can choose the area you want. That you are all very familiar with bolus making on the eclipse, and I don't need to explain that. Just for the workflow, we have this. So once the bolus is made, like you enter the thickness that you want and you make the bolus, you have to export this in dichromatic format that normally you do. The next thing is we export it in dichromatic. It's adequate, the structure set alone, but you need a reference CT also. So normally we include the images. The exported DICOM directly goes to the PC that has the slicer RT software, the slicer 3D slicer software, which we are using. We use for so many other things, as you know. Slicers 3D software, even for gel dosimetry from Kingston, they have given some plugins, and it's quite useful software. So once this is exported, the next thing is you go to Slicer 3D software. In the Slicer 3D software, you can import the dichromatic file. This is the Slicer 3D software where you go and say import the dichromatic, which is exported from your Eclipse. And you have to make sure your structure set file is there. So you can see that the structure set file is here, right? So that is there, that you have to make sure. And then you load it in your 3D slicer. And it will bring in all the contours that you have drawn there. But you don't need everything when you are making only the bolus. So what you do is you can delete the rest of the things from here. and have only the bolus in the slicer 3D. And you can now see the bolus alone is here. You can get a 3D model of that by in the slicer 3D. This is the 3D model of the bolus that you drew on the eclipse, right? So you got the 3D model of it. So once you have the 3D model, you have to now export it as .stl file. So for that, you need to go to the segmentation software of the 3D slicer, where you can export this to the folder that you want. And you can see that it is .stl file there. And I save it in a folder that I'm familiar with. And once it goes there, then you open the Cura software, the slicer software for 3D printing, which will convert this .stl to .g code, right? So as I told you, I use something called Ultimaker Cura, which is again free to download. You can download it, or you can use the one that is given by the 3D printer vendor. So when you buy 3D printer, you will get the slicer software that will convert the .stl to .g code. This is a very good one. This has more features, so I use this Ultimaker Cura. So once you have this Ultimaker Cura, you can load the one that you exported from your 3D slicer. And this is the same thing now you have, but I can change the orientation. This is the bed, 3D printer bed. It simulates the 3D printer bed, and you don't want to keep it straight and print. Maybe you would like to keep it horizontal. Then you can rotate it here, this one, in this software. And then if you look at here, this is where the resolution is. Like it is taken 0.16, and the infill, you see for bolus, I have to make 100% infill, right? Because it has to be a thick bolus. I cannot have any gaps in between. And then I convert it to .g code. It will tell you how much time it will take to do the 3D printing. Like for example, this one, it takes 12 hours, 52 minutes, and how much material it will need, about 51 grams, which will be 51 rupees, and 17 meters in length, right? So you can make sure that you have it. But if you feel that it's taking too long, you can reduce the resolution, and you have to make a call on it, which one you want, and you can do this. It now takes only 8 hours and 20 minutes, right? So this is about the bolus making. Now you transfer this G code file to 3D printer, it will print it for you. Now I'll show you again with CAD software. We will make a small holder for Marcus chamber. So if you're familiar with CAD, this is a child's play for you. And now I'm just learning. So for me, it's something very technical. So I'm trying to learn. You make a sketch and then convert the sketch into a block. And I made a block of 1.5 centimeter thickness here. So I make it 1.5 centimeter block. Then what I do is I take a point and have to have a place to keep, let me say, Marcus chamber. I don't know exactly the diameter of the Marcus chamber. I assume it is about 3 centimeter. So here I will make a 3 centimeter provision to place the Marcus chamber. Circular provision. So I first select the plane in which I want, and then go and take the circle and make I say 3 centimeter, assuming Marcus is 3. If not, I will have to change this. So now I can make a depression there where the Marcus chamber can go and sit. So how do I make a depression? I make about 7 mm depression there. So 0.7 centimeters. So I make a depression. You can see the depression at the moment. But still it is not complete. Your cable will come. So you need to make a path for the cable. So I will make a path for the cable there. And again, I go and select the plane in which I want to make that. I make a groove there. How do I make a groove? I just go and take that point and make a semicircle there. Right? I make a semi. You can do different methods. You can, as you think. And once I do that, then I finish it and finish the sketching, and then I go and extrude it, make a complete pathway for having the cable there. So I can go on from that to what depth I want to do that extrude. So it's approximately I measured it to be about 7.5 centimeter the middle of the chamber. Though you don't need to middle, you can still put it as 7.5. And now I have a groove for that. So this is how we do it. Once you have done this, the next you have to export this as you can save it, and I save it as a marker folder, and I save it in a folder that I have made it in the cloud, and then I can export this now as a .stl file. It's very simple. I just go and say select that, export here, and export it as a .stl file. It's already .stl there, so I just export it and choose the path where I want to save it. It's complete. Once this is complete, the next thing, as you know, is to straight away go to the Ultimaker Cura software, which will convert this .stl into .g code. So this is the same one, Ultimaker Cura, where we used earlier. I'm just repeating this. And for this one, then again, it is perpendicular. I can make it, I would like to have it horizontal here. So I make it horizontal to the bed. So this actually represents the heating bed than the 3D printer. And again, you can see I don't need this additional support. Like that is needed only when you have something which is 45-degree thing. You need something to support the 3D printing. There is nothing like that. In the earlier one I showed you had it, so I had to have the support. Now I don't have it. Let me say I make it as a slice it. For 3D printing, let me see how many hours it takes. It takes almost 3 hours and 29 grams of thing. So if you want to, if you feel you can make it more accurate and reduce that, and it takes about 3 hours and 51 minutes. So this is how you use it. But there is a lot of research opportunities. One of the reasons I wanted to talk about is when some students come and ask me, what can I do research? Some years ago, I used to say Monte Carlo, because there is almost everything you can simulate in Monte Carlo that is in medical physics, right? So Monte Carlo is any number of researches can happen. But now I find something very similar. If you have a 3D printer, there are so many things you can do. If you read this paper by from Peter Mac, the research opportunities in 3D printing is discussed, and you can make so many things in like CT, MRI, ultrasound phantoms, and templates, applicators. There are a lot of things you can do. One thing you have to be clear about, you have to understand which machine to use, what 3D printing filament to be used, etc. And let me conclude here saying there are exciting opportunities with 3D printing in radiation oncology and medical physics applications. And many people are working on it. There are already lots of papers, but if you look at the papers, it's all in the recent days, 2014 to 2021, 22, last 6-7 years. And there are still a lot of things you can explore. The 3D printing also becoming cheaper, and maybe the technology will improve much further, and there will be a lot of opportunities for us to work. And majority identified users so far have been successfully improved treatment delivery and according to dosimetric analysis. However, further work is needed. It's not complete. A lot of work to be done. Look at the efficacy of such users and larger clinical settings. 3D printing technology has some limitation like time, workflow, material used, everything. One has to really look at in detail all this when you want to jump into 3D printing for clinical applications. There is a learning curve. I have still not completed the learning curve. I'm learning. There are a lot of teething problems. I actually spoiled one heating bed. I'm going to buy another heating bed. And because it is a do-it-yourself, I can unscrew it and put it back. So I don't need to look for any companies, but the company is just helping me with advisors whenever I have a problem. There are a lot of things you have to learn, and you will learn it as you do it. And there are many people ask me of research opportunities. Many students ask me. I tell you, here is one where there is significant amount of research opportunities if you're interested in 3D printing. I would like to acknowledge my colleagues, Mr. Shivankar and Tapu, who helped me in the dosimetry and also support me in everything I do. And I would like to thank Dr. Timothy Pease and other colleagues in CMC Vellore for providing some of the material for presentation. Thank you very much for patient listening. I look forward to answering the questions, but there is a disclaimer that I am not an expert and I can tell you whatever I know. Thank you very much.
Thank you, Dr. Paul. Now, open to audience. If there is any question, you please put it in the chat box. There is one clarification from Mr. Samar Mandal. How to do dosimetric validation for brachytherapy 3D printed applicator?
Oh, that is okay. That's a very good question. But normally, when you do a template, the distances you can measure and see. That's not very difficult, right? The distances and the positioning and all you should be able to verify. But if you make an intracavity applicator, you need to simulate it with something to first check it. I would suggest, being a gel dosimetry fan, you can use gel dosimetry to do it. But I mean, I'm just joking. But you have to do some dosimetry method to do that. Okay, and is there any other question?
Yeah. There is another question from Reshma Bhaskaran. I saw some model, but they had undulations. Why desire smooth surfaces? I guess, what's your experience?
Okay, you would not, you would get, because it is additive manufacturing, line by line manufacturing, you will have those lines. For example, if I took 0.2, you will see the 0.2 millimeter lines there. But it's not very disturbing though. But you can reduce it to even 0.12 with the printer I have. If you go to very fine printer like stereolithography, you can make a very fine one. It will look like a company manufactured, regular manufactured one. But with 0.12, I'm sure you get very good one. I did something with 0.12, very small gadgets, because with 0.12, it takes significant amount of time. So for a smaller gadgets I use, it's really good. Really good. And you can do some finishing of the surface later on. If you're not very happy with it, there are several ways you can do it.
And also would like to know what's the time taken to print that bolus?
Oh, okay. Bolus, as I showed, is about 8 hours. You can see that with 0.2 and about 12 hours with 0.16 resolution. 8 hours is nothing. The cube that I'm showing you now on the screen, the IGOT cube, if I put 0.16, it takes 48 hours. Okay, so it's okay compared to nearly 48 hours. So I actually did this cube with 0.2. It took about 28 hours or so to print that. That was adequate for me. Like the distances are very, very accurate.
Sir, I have some one clarification still we get from audience. Is there any post-processing is required, sir, for after printing this 3D object?
There will be, for example, you see in the screen now, spine, right? The spine has a thing which nothing is below that. So when it 3D prints, how will it stay? So for that, it will give some support if you select the support. That support and all you will have to remove later on. It's very easy to remove. It takes maybe 5 minutes to remove that. So that will be the only thing. And if you feel the lines because of the additive manufacturing is disturbing, you can have some polishing done over that. Or you can even do a painting. You can just do a spray paint. It will look great with that. You know, the CMC hospital has several 3D printers in, they make prostheses and all those. And they do that. They just clean it up and put some paint and use it because it should look neat for the patient. Lalit has asked, what are the precautions to be taken when you want to use it, particularly in clinical setup. When you want to use it, you have to be very careful about whether the material you use is not giving a problem to the skin, particularly in immobilization and bolus making. You have to be careful. And when you use it in your lab, the 3D printing is by heating. I told you the nozzle gets heated to 200 to 240 degrees centigrade. For PLA, it is 200. For ABS, it's 240. So it will certainly produce some small fumes which you may not even see. People say ABS is little harmful because it is something like a real plastic. You shouldn't inhale it. You should have proper exhaust system, like fume system, if you are using ABS. This is what I have seen. So the other precaution which I learned in, I used to allow 3D print to happen because it takes more than a day and go for work. But somebody's put it on the YouTube. Don't do that. It can catch fire because you're working with 200 degrees centigrade. So after that, I do 3D printing while I'm home. I don't know how much it is right, but I don't want to take a chance when I work in a hospital. So I make sure that I oversee the 3D printing process.
And Samar Mandal, I would like to know what material will be recommended for brachytherapy application.
PLA is very good. It is easy to make. Just make sure that PLA, when you, the only problem is when you apply into the patient, like natural cavities, you need to sterilize it. So your sterilizing method, if you put it like heat sterilization and all, it will deform, right? So you have to have a sterilization method which will not spoil it. So that you have to be a bit careful. Otherwise, it will even deform the shape if you heat it too much. One interesting thing is one group have used 3D printing as a shell to make bolus. What they have done is they have made a 5mm shell and poured resin into it and gel into it and made the bolus and then broke the 3D printed shell and took it away, and they got the shape of the shape they wanted for the bolus. So there are so many things you can try, and the literature gives you a lot of ideas if you go through. There are a lot of research opportunities here.
And Reshma Bhaskaran would like to know, you have mentioned about some accuracy.
Yes.
Is that accuracy of converting CT to 3D models? Any other uncertainties? Would like to know that.
Uncertainties usually only could happen with ABS. For example, ABS is very material which is tissue equivalent, and normally even the ABS, I have to be very frank, the slabs I printed, actually I printed like 2mm thickness. When I actually measured with the digital caliper, it was 1.5. That didn't happen for me with the PLA. When I printed with PLA, if it is 2mm, it is 2mm, right? Only the second decimal or third decimal error there. But I got more error with ABS. So ABS is, in my opinion, is not useful when you want to have extremely accurate thing, right? Then probably you will have to find a method of printing accurately with the ABS. The one I used, it didn't provide me a very good, but PLA was very good. And the other errors that could happen is like your 3D printer, because of repeated use, can lose some accuracy. You have to make sure your 3D printer is in good form. Maybe you can do some tests and make sure that the movements are excellent, because it's just a motor and movements with belt and lead screw. So you have to make sure that those are good.
And Chantaram director has, is it possible to create heterogeneous phantom, and how can we process it?
Excellent question. I didn't touch upon that. You can do that. There are a couple of ways you can achieve that. For example, if you want to, like you saw that CMC Vellore Phantom, you can put gel into it, you can leave cavities, and you can fill the cavities later by making it heterogeneous. So you can make it heterogeneous. That is one way. And nowadays, you get 3D printer with where you can have more than one coil and more than one filament, which will actually, I think it will also speed up the process of 3D printing, and it will also, you can have different material, one ABS, one PLA, and plan it accordingly. But I'm not sure how the software works there. I have to investigate. I have not worked with one, so but we'll have to look at it, whether that will make 3D printing much faster, and whether you can do the heterogeneous phantom that you want with that. But it is possible. That is one topic for research interest.
That question, any possibility to create vaginal or uterus mold gynecologic malignancies, and any method to measure for a patient by Vinay's side.
It is certainly possible. You can make a 3D printed mold and put graphchromic films around it at a position and see the distribution of dose. People have used graphchromic films to study some of the dose distributions in the 3D printed ones, or you can use gel. Gel is one that you can use. And making a vaginal mold is rather simple. I can make it in 10 minutes. Okay, so only issue that is you have to make sure that it doesn't affect the patient. The PLA in contact with patient surface, whether there is any reaction or things like that. That we'll have to check. I'm not clear about it. I haven't seen a paper on that, but we will have to look at it. Otherwise, making one is not difficult.
And Samar Mandal, I would like to know what is the infill in 3D printing?
See, infill is the concept that they use. I think I showed you one. When you want to do, for example, a 1 centimeter thick block, why to waste material for the entire 1 centimeter? You want the top surface, bottom surface, side surface plain, and whatever inside, you are not really bothered. So that infilling only except for the strength. So infilling, they make something, sorry, I will share it again. Okay. The infilling, what they do is, I showed you here. This is what you will see. And the top layer again will be a plain layer. So in between, you get this like a honeycomb structure or things like that. So depending on what percentage infill you say, this will be made. If you say 20% infill, this is how it will look. If you say 50% infill, it will be much closer. If you say 100% infill, it will fill up completely with PLA or ABS or whatever material you use. This infill is brought in to reduce the time and the quantity of the material that you use.
Sir, I'm not able to see the screen, sir.
Oh, sorry, I have to share it again. Sorry. I will share it again. Give me a second.
Yeah, please.
Which screen do you see? You don't see that, right? You see the wrong screen probably. Okay, I will undo the sharing and then I will have to share again. Sorry. Do you see that now? Do you see my screen?
Okay, sir, no problem.
Okay, I can share it now. I think there was something else there behind which I didn't see. Okay.
Yeah, now.
I'll go to the, I'll keep it like this and show. Okay. So this is actually the infill that I was mentioning. It is not fully filled with PLA, right? There are structures like this, cross structures made. And there is another paper from Peter Mac where they used this to about 90% or so to make different structure phantoms also. I haven't understood that paper completely, so I didn't bring it up in my talk. But you can go and look at it. This is by the same author, who did the review of the 3D printing for so many opportunities. But he has done another paper on this. You can go and look at it. But this is the infill. That now you can see it's only 20% infill. But when I made this thing, it was fully filled with 3D printed material, right? 3D printing material.
Okay.
Any other question? Or?
Is there any other question from participants? Okay, sir, I have one clarification.
Yeah.
Hello?
Yeah, I can hear you.
Yeah. Sir, as the role of this additive manufacturing technology plays a vital role in radiation oncology, as you mentioned, also as it becomes more common, and there might be some controversy due to moral or ethical or legal issues. So at present, is there any regulatory guidelines, sir? Any
No, as I know of, no, as I know of.
Any new things comes, there will be some controversial thing will be arising.
Actually, I wanted to avoid stating that because when somebody asked me whether they can make a vaginal mold, my next thing to say, as long as the regulatory people allow, you can make. But I kept myself away from that statement. But anyway, like we are all physicists, we are responsible people. We know how responsibly we should use it. So all the research that we see now, nobody has just jumped into anything. They are doing trials, they are checking with phantom, they're checking. So I think people will take all the care to really use it. But there is a different method, new method, interesting method. So people should use it, but how safely we use it left to us.
Because any new technology, any new thing comes, always there will be some controversy.
Yeah.
Even that nanotechnology, when comes, so many criticism, controversies. That's why I asked.
Yeah. Okay.
So many people have commented very informative talk,
Thank you.
excellent
Thank you.
presentation, more informative. Is there any more questions from audience?
Otherwise, I would like to stop sharing and.
If no more questions, can I summarize?
Yeah, please go ahead. I will stop sharing.
Okay. So from, I hope everybody is commenting great presentations, like good comments is coming. Okay, from today's presentation, it is clear that the 3D printing plays important significant applications in healthcare, particularly in medical physics and in radiation oncology. There is more evidence that the 3D printing technology can be extremely useful in creating innovative research and the clinical tools in radiotherapy. But I think care needs to be taken to ensure that those calculations involving these devices are accurate. Anyway, we'll wait and see a lot more changes which may happen in future. Okay. With this, I thank the speaker, Dr. Paul Ravindran sir, for his wonderful, very informative, latest technology development taking place in our medical fields, particularly radiation oncology field. I also thank all the participants once again for attending this lecture series. I thank one and all for
recording in progress.
Attending this series. Thank you.
Thank you. Thank you very much, everyone. Thank you, Dr. Velmurugan. Thanks to Bhatt. Bye-bye.